Simulation of a single phase diode bridge rectifier with R load and RL load by using pspice. Okay. So here, open pspice schematic. So from pspice schematic, take one source V sine. So V sine and then place on a drawing sheet like this. Okay. After this, enter in here. Diode name is called D1N4002. Like this, place on drawing sheet. Okay, and Control R, rotate like this. Place 4 diodes, single phase diode bridge rectifier, bridge tab. Okay, bridge tab, single phase diode bridge rectifier. So these are the different types of diodes are connected like this. So connect these diodes here in this way, and also this connect this diodes, this diode to this diode, and here connect, arrange properly this diodes, and connect in this way here also. And take one resistor from PSpice library. First, resistive load. First, we have to execute this experiment, single phase diode bridge rectifier. So, by taking resistor, connect this voltage source to one pole and this another pole. And this resistor, the voltage across the resistor connect like this. Okay, in this way, from here onwards. Connect the voltage across the resistor, connect the load across the diodes like this. This is called bridge configuration. Single phase diode bridge rectifier. Okay. So in this, take one ground and connect here. Take one ground and connect here. And also introduce one dummy voltage source in series with the voltage source, supply voltage. Take one VDC, press Ctrl R, introduce one dummy voltage source here. Place, then connect one marker. Connect this by using a wire. And next, similar way, voltage across the current flowing to the load. To find the current flowing the load, so introduce one dummy voltage source here. Connect this dummy voltage source. The voltage source voltage is called 0. Okay, and this is a resistive load and change the resistance to 100 kilo ohms, 100 ohms. Change resistance to 100 ohms. Okay, and save alter and press OK. And open vSyn. Open vSyn. So in this vSyn, DC is equal to 0, AC is equal to 0, Vf is equal to 0, and V amplitude is equal to, for example, 230. Amplitude 230 volts is supply. For example, frequency is equal to 1 kilohertz. Frequency is equal to 1 kilohertz. Save alter and then OK. This is the design of a single phase diode bridge rectifier with R load, resistive load, and numbers and labels. Interview in here there are numbers, label change in numbers. Here label is called 0. Ground is always 0. And then connect here between source and uh, voltage source and dummy voltage source, enter label 1. And then here 0 is over and 1 is over, and then enter label like 2. Okay, and then next here the label label 3. Okay, and after this year also 3 is over, then 4 label. So this is up to year, this is called 3 only, then year 4, and then in between these two, 4 is over, then 5. So interlabel and this. It's clear. And go to analysis, setup, enable transient, make a tick mark on this box, and press transient, open transient, and print step is equal to 0 nanoseconds, so don't change, no change. So here time, final time is called 2 milliseconds because of our frequency is called 1 kilohertz. That's why, so 1 by 1 kilohertz is nothing but time, that is equal 1 millisecond. So that's why it give 2 milliseconds, greater than 1 milliseconds, that is equal to give 2 milliseconds. And so okay, close. Okay. So then if you want to generate the voltage directly without writing the expressions, take one voltage mark here, markers, mark voltage differential. So connect across the voltage source, resistive load. Mark voltage difference means this is the voltage across the load. And similarly connect one voltage marker before dummy source, that is called across source. Okay. So like this, single phase diode bridge rectifier is designed. And if you want to generate this type of color, yeah, enable like this. And if you want to generate color, so press like this, same color. So like this, single phase diode bridge rectifier is designed, and analysis also, settings, analysis settings also adjusted like this, 0 seconds, 2 millisecond final time, and then close, and press save icon. This is called a single phase diode bridge rectifier. Single phase diode bridge rectifier. Single phase diode bridge rectifier. Okay. Then save. After save, so then simulate. Then we will get voltage waveform and voltage across the load like this. So here, this is called supply voltage waveform. This is called voltage across the load. Okay. Connect one voltage source, voltage marker here like this, and connect here. This is called voltage marker analysis. Here markers. Mark voltage differential. Mark voltage differential. Connect across the resistor like this. So go to markers. That is called second one. Mark voltage differential, and place on here across the resistor. Okay. You have connect place here and then minus here. So then simulate. Then we will get full wave output, full wave rectifier, single phase diode which full wave rectifier. Okay, then this is our output voltage waveform. Go to properties and change the width of this waveform, and so this is our output voltage waveform, full wave rectifier output voltage waveform, and this is our input voltage waveform. Input voltage waveform, and this is our, so that is called negative is also converted into positive off cycle. Negative, that means current flow into the load is called positive. That is called voltage across the load is also always positive, unidirection. That is, this is the voltage across the load, resistive load. So by using this markers proves we are getting the voltage across the source and load. So by writing the expressions also, we will get this voltage and current. Okay, remove this. So here, source is connected between 1 and 0. Source is connected between 1 and 0. So if you want to get the voltage waveform, write expression V of 1 comma 0. So if you want to know the voltage across the load, write expression V of 3 comma 5. So for that, go to simulate, first simulate, and the new window appear like this. In this window, go to trace, add a trace, add a trace, and write the expression here. So what is the expression means? V of the load is connected between 3 and 5. That's why. So V of 3 comma 5. Write this expression. Total trace expression. Here write V of 3 comma 5. 3 comma 5. Like this. And then okay. So this is our voltage, output voltage waveform of single phase diode bridge rectifier, single phase full wave diode bridge rectifier, full wave rectifier. So like this we will get the voltage, okay, of a single phase full wave diode bridge rectifier. And also if you want to find the source voltage V1 and 0, write expression in this trace box, trace expression right here, V of 1 comma 0, V of 1 comma 0, and then like this, this is the output, our input voltage waveform, sinusoidal input voltage waveform. Okay, by writing the expressions, V of 1 comma 0, that is called the source is connected between 1 and 0, that's why. So we have to write V of 1 comma 0. If the load is connected between 3 and 5, that's why we have to write V of 3 comma 5. So in this way we have to write. And then next, how to get this current waveforms. So this is called I of V2. Okay, I of V2. So how to write here I of V2 means go to trace, simulate, first simulate, and then new window will appear like this. Trace, add trace, and I of V2. So right here I of current expression, I of V2 voltage across already is here. So no need to write here. I of V2 is also available. So I of V2. So this is our source current waveform. Okay, source current waveform. So in this way we will get source current waveform. Similarly, if you want to find the load current waveform, this is called I of V3. Okay, so go to trace, add trace, I of V3 is called, this is called load current waveform. Here 10 amps, maximum is called 10 amps. So this is our source current waveform. So red color is called source current waveform, and this is called, this color is called, green color is called load current. Understood? So this is our output voltage, out source load current flow into the load. So here up to maximum 10 amps. Maximum peak is called 10 amps, 0 to 10 amps. So in this way we have to find the voltage and current. Okay, voltage across the load and voltage across the load and current flow into the load and source current and source voltage and load voltage. And then next to find how to find average value and RMS value. Okay, go to analysis and simulate first, and then window appear. Go to trace, add trace. So then here average AVG in right side boxes. Select this icon, average AVG of so average voltage of 3 comma 5. We have 3 comma 5. We have 3 comma 5. We have 3 comma 5. This is average voltage. So like this we will get. So approximately 60 volts. 60 volts we are reading average voltage. Okay. Average voltage of output voltage is called 60 volts. By simulating like this we will get. So this is called 60 volts. Approximately 60 volts we will get average value of DC voltage. Okay. And then similarly RMS value, how to find RMS value means so go to trace, add trace, Here RMS in the right side box expressions function and functions. This is called RMS. Take RMS value. Average value is our, and then next RMS. RMS. So RMS of V of and here load is connected between 3 and 5. That's why average value of RMS value of V of 3 comma 5. RMS value of V of 3 comma 5. Then close bracket. Then okay. So this is called RMS value. Red color is called this. So RMS value. This is the RMS value. So approximately this is the voltage. For example, enable toggle cursor. Find here by using toggle cursor. Mark here approximately 67 volts we are getting. 67 volts. Okay. So this way we have to find average value and RMS value. Okay. And here next for this output voltage single phase diode rectifier R load. Single phase diode rectifier for R load. So what is the voltage across this V of 3 comma 5. Load is called V of 3 comma 5. So enter like this. This is called voltage across the load. Average value of voltage across voltage across the load. Output voltage, output waveform across the load. And then here how to find the harmonic analysis. What is the total harmonic distortion THD? What is the total harmonic distortion THD for full wave rectifier? Okay, so go to analysis, setup, enable transient, and also enable Fourier also. Okay, center frequency, for example, 1 kilohertz. Okay, number of harmonics maybe 9 or 10. Okay, and then V of output varies. This is called V of is connected between 3 and 5. V of 3 comma V of 3 comma 5. Like this, and then simulate. Right here expression V of 3 comma 5. Close this expression. And then press FFT here. So this is called different types of harmonic voltages. Okay. Enable toggle cursor and the press here. What is the frequency here? For this for 25 x-axis is called 25 edges. So 58.452 mark label like this. This is the voltage for corresponding frequency. Here what is the frequency? Here means 2 kilohertz. For 2 kilohertz 40.68 is called harmonic voltage. 2 kilohertz, this is the voltage, harmonic voltage, second harmonic voltage. And then corresponding similarly 4 kilohertz, what is the voltage? It's called for 4 kilohertz 7.975 harmonic voltage. That means even order harmonics are present in this output voltage waveform. And then similarly here press here also and mark label. So 6 kilohertz. For 6 kilohertz, 3.0847 is the voltage. For 8 kilohertz, mark label. So 1.6 is the voltage. So I like this different harmonic spectrum. That is called spectrum is analyzed in this way for different types of harmonic voltages. Fundamental harmonic voltage and second harmonic voltage, fourth harmonic voltage, sixth harmonic voltage, eighth harmonic voltage. And this full wave rectifier is having only even order harmonics voltages. Okay, even order harmonic voltage. So corresponding, these are the different types of voltages. Okay, after this, go to view output file, and then total THD. Here total number of harmonics is called 9. Total number of harmonics are called 9. That's why we have 3 comma 5. The load is connected between 3 and 5. Na? That's why. So number of harmonics under analysis, we have designed the settings like this. Setup transient. So center frequency 1 kHz. Number of harmonics are 9. That's why harmonics is number of harmonics are generated in the output file is called 9. So total harmonic distortion is equal to total harmonic distortion. THD is nothing but this is the total harmonic distortion. THD is equal to 2.752 into 10 to the power of 4%. So in this way, we are finding the total harmonic distortion of a single phase diode bridge rectifier or full wave rectifier. Single phase diode bridge full wave rectifier. So for resistive load and inductive load, that is called RL load. This is called source voltage. V of is equal to 0, V amplitude is equal to 100, and frequency is called 1 kHz. So then your resistance is called 0.5 and inductance is called 6 millihenry. So across R and L, connect one voltage marker, go to markers and mark voltage differential. Connect this one side of this resistor and connect one negative marker at another side of inductor. Okay, connect like this and then simulate. So this is the output voltage across the resistive and inductive load, RL load. The voltage across the RL load is called like this. And this in this analysis setup on transient enable Fourier series and center frequency 1 kHz and number of harmonics of 9. Okay, this output varies V of 3 comma 6. So that's why here this load is connected between 3 comma 6, 3 and 6. That's why. So we have to enter like this. We have 3 comma 6 and then okay, and enable Fourier, and then okay, and then close, then simulate. So go to view, and then output file. In this output file, number of harmonics are called 9. So for 9 harmonics, so this is the total harmonic distortion, THD for RL load. THD for RL load is called 1.059 into 10 to the power of 4. So previous one approximately 2 point something volt into 10 to the power of 4. So here but less, total harmonic distortion is less for RL load. Okay. And then next we have to execute with filter, total harmonic distortion with filter. So we have to analyze with filter by connecting LC filter. By using LC filter, take one inductor, connect your inductor in between these two. Here, connect inductor. Connect inductor in series and capacitor in parallel. Remove this terminal like this. Place one inductor in this way. Connect inductor in series with the load. LC filter, by taking LC filter. Similarly, by connecting capacitor, connect one capacitor in parallel. So rotate control R. Place this marker and place here. So in this way, connect one LC filter. For example, this is inductance is called, for example, inductance value 30 millihenry. 30 millihenry, 30 millihenry. mH. Save order, okay. And the capacitance value is called, for example, 320 microfarads. 26 or 325 microfarads. Save alter, then okay. And here labels are like this, labels. So here 0, 1, 2, 3, here 4, and here label is called 5. 5 enter label here 5. 5, and here change label to 6. 6, and here 7. 7. Okay, so like this, change the labels on schematic circuit diagram. So 0, this is called 0 ground, and this is called 1 and 2, and here 3, and here 4, 5, 6, and 7. Like this, labels are on each equipment, each device we are connected in this way. 0 and 1, the source is connected. 1 and 2, this source. In between 0 and 1, AC sources. In between 2 and 3, this diode is connected like this. Okay. So then go to analysis, simulate icon this. Then go to simulate. Then icon. The voltage across the RL load is called connect LC filter. L is equal to 30 millihenry and C is equal to 325 microfarads. Like this connect. And then connect the load. The voltage across the load is called plus. This is called voltage across the load is called RL. Across the RL is called load. The load voltage. So connect one voltage marker here, that will be display source voltage. Then simulate. So this our input voltage. Okay, properties, go to properties, width, change width. This is our input supply voltage. So the supply voltage is called 100 volts. That's why positive peak and negative peak amplitude is called 100 volts. And this is our output voltage. Okay, this is our output voltage waveform. Because of filter, this changes the output voltage waveform changes like this. So then press FFT, and then harmonic voltage. This is called harmonic voltage spectrum. So in this, this is called our input. Only fundamental harmonic present. Fundamental voltage, harmonic voltage is only present. Enable toggle cursor, and here what is the voltage is called? What is the voltage? 100 voltage. Okay, fundamental harmonic, our input sine voltage waveform is 100 voltage only. Okay, for 60 edges, our input frequency is called 60 edges. For 60 edges, so this output voltage waveform, output voltage is nothing but 60 edges. 100 voltage, 60 edges. For 60 edges, 100 volts. So this is our input, and then this is our output. Corresponding this output mark label. So here mark label. Remove this. Mark label here. Mark label by using this toggle cursor and mark label like this. So 120.4945 edges. The voltage is called, the harmonic voltage is called 39.5. And then go to view, and then output file, and the total harmonic distortion THD, total harmonic distortion 7.36 into 10 to the power 1. That is called 73%. So like this, the ripples are reduces and harmonics also reduces. This is about with filter. Okay, a single phase diode which rectifier with filter.